Good morning, class. Here's chapter 1 review, functions and models. I'm going to put this in slide mode to get started with this. So let me close this up. 4 ways to represent a function: verbally by a description in words, numerically by a table of values, visually by a graph, and algebraically by an explicit formula. I hope you remember the function machine: input x, output y or f of x. So the pair x comma f of x, where x is an element of the domain. This looks like an epsilon. It is an element of, it's read, an element of. It's in the set theory. When we deal with functions, we also deal with the VLT, vertical line test. A curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve more than once. A function is considered increasing in some interval if f of x of 1 is less than f of x of 2, then x of 1 must be less than x of 2. And if f of x of 1 is larger than f of x of 2, x of 1 must be less than x of 2. That is in the case of a decreasing. In other words, here's one easy way to tackle this concept. So when we say increasing, when x goes up, when x gets larger, y gets larger. When we say decreasing, x gets larger, y gets smaller. That's simple. HLT, if we have a one-to-one function, it has to pass not only the vertical line test, the VLT, also horizontal line test, HLT. A function is considered one-to-one if and only if no horizontal line intersect its graph more than once. Therefore, it has an inverse. And as far as the inverse is concerned, f inverse of f of x, that means f inverse OF equals x, f of f inverse equals x, as long as x is in A and x is in B, in this case, the domain of each one. And so one way to check whether two functions are inverse of each other, you look at their composite function must be equal to x. Even function by definition, if f of minus x equals f of x, it's even. If f of minus x is minus f of x, is odd. So in the case of an even function, it's symmetric with respect to the y-axis, odd function with respect to the origin. WRT with respect to y-axis for the odd one with respect to the origin. 0, 0. When I find the domain for this function, if you recall, although you can simplify it as x plus 2 times x minus 2, and you can cross out x plus 2. Still, it is important to know that this has a domain which is not all real numbers. I'm going to discuss it further in a little bit. X can't be -2 because it makes the denominator 0. And this is one format to write it. And this is the interval notation. What about this one? You factor the denominator. You want two numbers, the product is -10, the sum is +3. That would be 5 and -2. Therefore, x can't be -5. X can't be +2. And in an interval format, here's how we write it. -∞ to -5, union -5 to 2, union 2 to infinity. Notice -5 and 2, all of them have parentheses, because if it's included, they take a bracket. So if we put a bracket, that means -5 is included. Now, to finish this concept, as we look at this function, is it equal to that? And the reason we write it is because the numerator can be factored into x minus 2x plus 2, and you can cross out the x plus 2. Are they equal? That's the concept. So when we do the factoring, we can drop the common factor of x plus 2. However, it remains that x can't be -2. So it's not that f of x is always equal to x minus 2. No, f of x equals x minus 2 under this condition, which means if you were to graph this is a line. If you graph the line y equals x minus 2 is just a line, right? However, if you graph this, it's a line with a hole at x equals -2. In fact, you can plug in -2 here, becomes -4. So this one would be having a hole with coordinates -2, -4. Again, how did we get the y coordinate? If you plug in -2 into this, you get -4. That's its y coordinate. All right, we want to determine whether each represents a function which is even or odd, and reminding everybody about the definition. So basically, for even and odd, basically evaluate the function f of minus x or g of minus x and upset. Let's plug in minus x, f of minus x. So replace the x with minus x. And as you can see, this becomes minus x to the power of 5. This becomes minus x. So you can take the common factor of -1 out. And therefore, when you compare these two, it becomes minus f of x, which makes it an odd function. Let's do it for g of x. Since the exponent is even, that becomes x to the power of 4. And as you can see, it's identical to g of x. Therefore, g is an even function. Let's find h of minus x. So this becomes minus 2x. This one becomes x squared. So this minus remains. So minus 2x minus x squared. And when you compare this to the original function, is it equal to the original function? No. Is it equal to the opposite of that according to this? No. So it's neither even nor odd. We are given the following function, the following graph, and we want to see where the function is increasing, decreasing, so on and so forth. Increasing, in short, when x goes up, y goes up. Decreasing when x goes up, y goes down. And constant as x changes, y remains the same, doesn't change. And so look at this part. As we go from left to right, obviously x increases, so does y. And so from here to here is from -4 to 0. You can write it in this format or interval format, inequality format or interval format. Where is the function decreasing? You can see it in this area, also in this area. And so we put this one and this one together with the union. This goes from -6 to -4. This goes from 3 to 6. And we put a union in between. Now, where is the function constant? As you can see, a line which is parallel to the x-axis and has an equation. If you were to make up an equation 0, 4, 3, 4, you can see it's y equals 4. That's a constant from here to here. Could somebody read this question for us, please?
I'll read it.
Please, go ahead, Chris.
All right. Example 4, section 1.2, math model is essential functions. A, as dry air moves upward, it expands and cools. If the ground temperature is 20 Celsius and the temperature at a height of 1 km is 10 Celsius, express the temperature T in Celsius as a function of height in kilometers, assuming that a linear model is appropriate. B, draw the graph of the function. What does the slope represent?
Perfect. Thank you so much. So let's read the question and see what's given. As we go through the process, we notice the following. The pair x comma y, now we have h comma t. H represents the height, t represents the temperature. So again, normally we have x comma y. X is the independent and y is the dependent variable. In this case, h comma t. So the ground temperature is 20, so that means 0, 20. 1 kilometer, when the height is 1 kilometer, the temperature is 10. Again, the way they're asking, we want temperature as a function of height. So in order to come up with the equation of a line, a linear function, we remember that m is change in y over change in x, rise over run, the average rate of y with respect to x. Now, instead of y, so y sub 2 minus y sub 1 becomes t sub 2 minus t sub 1. X sub 2 minus x sub 1 becomes h sub 2 minus h sub 1, and we plug in. Now, there are different equations of lines, and normally we use point slope, and then you solve for y to get to slope intercept form. However, y equals mx plus b. In this case, the y-intercept, or I should say, the t-intercept is given. So instead of x and y, remember, we are going to use h and t, so the equation becomes t minus 10h plus 20 because this is the constant. And so the next one, so that is the function. The next one is asking us to graph this. Well, you need a couple of pairs, so you can just use those pairs. Or if you want to go with the intercepts, this is one of them, 0, 20. And if you set this one equal to 0, you get 2, 0. And so y-intercept, and I put it on purpose. Let me use it. So that would be the t-intercept. And x-intercept, that would be the h-intercept. And the graph looks something like this. The slope is m equals negative 10 degrees Celsius per kilometer. By the way, as far as the units, you look at this fraction, the units of the top over the units of the bottom, the units of the numerator over the units of the denominator. That's how we get degrees in Celsius per kilometer. It represents the rate of change of temperature with respect to height. What is the temperature at a specific height? Whatever they give us, in this case, 2.5. That means you have the formula and you want the T at h equals 2.5. Replace the h. And it gives you minus 5 degrees Celsius. All right, making up new functions from the old functions. If this is your regular function y equals f of x, and you assume c is a constant, which is a positive value, so f of x plus c takes us c units to the left, f of x minus c takes us c units to the right, f of x plus c takes us up by c units, and f of x minus c brings us down. If we multiply it by c, it stretches by a factor of c. If it's 1 over c, it shrinks it. And if you have f of x versus minus f of x, that means reflected with respect to the x-axis. Here's the reason. Because if you put a negative sign in front of the f, you are negating the y value. On the other hand, if you put it in front of x, in other words, f of minus x, so if assuming x is positive on this side, on the right, if x is positive, then minus x makes it negative. Remember, that's really not the case. Minus x means the opposite of x, whatever it might be. So that makes it reflection with respect to the y-axis. So this is some information about transformation. Algebra function, f plus g means f of x plus g of x, f minus g means f of x minus g of x, f g means f of x times g of x, and f over g means f of x over g of x. Assuming the domain for f is a and for g is b, assuming that's the case, then the domain of all of these functions is the a intersection b. It's the intersection of the two, meaning whatever is in common. So if there's a restriction with a, if there's a restriction for b, you have to consider both of them in this case. Now, for all of them, except the last one, this one not only has this restriction, also g, the denominator, cannot be 0. And let's also add the composite function f of g means f of g of x, u of means g of f of x. And this concept of an inverse function that was discussed in the beginning. So transformation of functions. What about an absolute value of a function? If y is absolute value of f of x, by definition, absolute value of f of x is f of x if f of x is larger than or equal to 0, and it's minus f of x if f of x less than 0. And before we continue, I want to remind you of the definition of an absolute value itself. And then I'm going to clean this up. Recall, absolute value of x by definition is x if x is larger than or equal to 0, minus x if x is less than 0. So what I want you to pay attention to is that obviously everybody knows square root of 5 is 5, because by definition absolute value means distance from 0. So what we are doing, what this means that we are here. And what it says, if it's inside the absolute value, you see a positive value, just repeat that. You can drop the absolute value and write it. On the other hand, what about the absolute value of minus 5? We know it's 5, but the meaning of it comes from the second part. And I want you to know what this means. This means write the opposite of whatever you see here, which of course makes it positive 5. Why is this understanding important? Because if you have numbers, you know how to deal with them. But what if you have a variable? And so you need to understand this concept with x versus minus x. I'm going to move on. So let me clean up this mess. This was just to refresh everyone's memory about the concept of an absolute value. All right. So if we want to graph y equals absolute value of x squared minus 25, what do? Here's the process, everybody. We're going to graph it as follows. The part of the graph of f of x that lies above the x-axis doesn't change, remains the same. The part that lies below the x-axis is reflected about the x-axis. So if I want to graph this, first I'm going to graph f of x equals x squared minus 25. And I hope everybody remembers just, this is x squared, and then you go down by 25 units, and that's the case. Now, if you look at the blue part, it's above the x-axis, and according to this, it doesn't change. But the yellow part is below the x-axis, so you flip it over. Now, the graph becomes this. This is the graph of what we want, y equals absolute value of x squared minus 25. We want to graph this. And to graph this function, first, let's graph the function y, or y sub 1 equals square root of x. Everybody should remember the graph of all essential functions, all the functions that we have studied in the past. I'm going to just quickly write some of those, and then I want to make sure that you guys know that. So if you don't remember them, you want to go study them. Y equals x squared, y equals, well, of course, y equals x, y equals x squared, y equals x cubed, y equals, this is y equals square root of x, y equals cube root of x. Looking, again, this is obviously what I'm graphing is not to scale, but looking like that. So these are some of essential functions that you should know. Y equals absolute value of x looks like this, looks like a V shape. And there are more functions, but just for now, this is good enough. So let's continue. So the very first step is to graph the basic function y equals square root of x, and we're supposed to know. Now it's -1. That means move this down by 1 unit. So the same function goes down by 1 unit. Now, this portion is above the x-axis and it's not going to change. This portion is below the x-axis and it will flip over it becomes something like this. That would be the graph. So the blue part remains unchanged. The red part flips over. That's how you graph an absolute value function. We want to find the domain for this function. As you know, when the index is even, what's underneath the radical must be non-negative. That means x is larger than or equal to 0 or 0 to infinity. On the other hand, since we are added, if we had y equals cube root of x, the domain could be minus to positive infinity in case, okay? And so for part G, then 2 minus x must be greater than or equal to 0. And that means 2 greater than or equal to x, or x less than or equal to 2, or negative infinity to 2. That would be the domain for the g of x. Now, f plus g of x is obviously the sum of the two. F over g of x is square root of x over square root of 2 minus x. And if we want to find the domain for each case, first we look at their intersection. So what is the intersection of A and B? It's easier to start from here. You go from negative infinity to 2, and over here from 0 to 2. And I hope you realize, if you were maybe, if we try it, it makes it easier to understand. If we look at this one, is from 0 to infinity. And in this case, anything to the left of 2, and 2 is included. So what's in common? 0 to 2, and the endpoints, namely 0 and 2, are both included. That's why we use brackets. What about this one? The same thing, but we want to be careful since we are dividing by g. Whatever makes g 0 is out. So what makes g 0? X equals 2. So the 2 is out. So the difference is, now use a parenthesis. 0 is included? Yes. 2 is included? No, not in this case. All right, given f of x is square root of x minus 3, G of x is x squared. H of x is x cubed plus 6. We want to find f o g o h. So let's do them in a couple of steps. We can do f o g first. So what is f of g of x? That means in this function, replace the x with g. So put the g of x here. So that's f o g. Now, f o g o h, how do you get that? That means wherever you see x, put the h function. So x squared, parentheses squared. Think about this as parentheses. Something squared, right? It's going to replace it there. You don't even have to, you can simplify it or not, but that's not the point here. Obviously, it's not too bad. You can raise it to the power of 2 and combine the constants, but anyways. All right, let's remind everyone of exponential functions. Y or f of x equals a to the power of x. A is positive and a can't be 1. When the base b or a, in this case b or a, it makes no difference, is between 0 and 1, we have an exponential decay. When it's larger than 1, we have an exponential growth. And of course, if it's 1, it's a horizontal line. That's why it can't be 1. And the exponential rules, everybody remembers the zero exponential rule, product rule, quotient rule. If you have a fraction, you want to raise it to a power, you do both. Negative exponential rule. Again, negative. Pay attention to these three. They are all negative exponential rules. Basically, these two, what they tell us, if you have an exponent which is negative, move it. If it's up here, bring it down. If it's down here, bring it up, make it positive, and in this case, flip it over. And this is called the power rule. Now, in the case of exponential functions, horizontal asymptote is the x-axis, or y equal to 0. There is no vertical asymptote. The y, this is for the basic function. The y-intercept takes place at 0, 1. The x-intercept is non-existent. Domain, there is no restrictions, all real numbers, and range is from 0 to infinity. 0 is not included. So if b is positive, if the base is positive, then the function becomes increasing. And as you can see, the limit of f of x as x approaches infinity is infinity. The limit of f of x as x approaches minus infinity is 0. We will discuss this in the next chapter when we go over the concept of the limits. When it's decreasing, then the limit of f of x as x approaches infinity is 0. And that is the definition of a horizontal asymptote, by the way. And the same thing here, right? So this means this. Horizontal asymptote has the equation y equals 0. And the limit of f of x as x approaches minus infinity, as we go to the negative infinity, it blows up to infinity. And what you're looking at, it's what you have learned in algebra known as the end behavior. So let me write that, so because it's important to remember what we learned in algebra. So this is called, this concept in algebra, we called it the end behavior of a function. When we wanted to graph it, we needed to know that that would be helpful. All right, so we want to graph the function y equals 1/2 e to the power minus x minus 1, and we want to go and start with the basic. And y equals e to the power of x is that the exponential growth we showed in the previous page, regardless of what the base is. If the base is larger than 1, looks similar to that. The larger the base, the closer to the y-axis, okay? But they basically look the same. So we got e to the power of x. Then the next one is e to the power of minus x. So if you're changing x to minus x, it flips over with respect to the y-axis. So that concept of an exponential decay that was discussed. So we got e to the power of minus x. Now we want to multiply this by 1/2. That means the y coordinate for every point gets smaller by a factor of 1/2. And so we compress the graph vertically. So this 1, for example, now 0, 1 becomes 0, 1/2. So this point zero, 1/2. And so minus 1. So this function minus 1 is going to go down. It's going to go down by 1 unit. So shift the graph down by 1 unit to get to this. And so what happens is that now this point, there's a different colors. Now this point has shifted here. With coordinates 0, negative 1/2. So what did we have as the horizontal asymptote here or here or here? All of them, the horizontal asymptote was the x-axis, which is y equal to 0. It has gone down by 1. And so it has created a new horizontal asymptote, y equals negative 1. Therefore, the changes that the domain for this one, this one, this one, this one, the domain hasn't changed. It's all real numbers. But the range, go back to this one, was 0 to infinity, 0 to infinity, 0 to infinity. This one, the range is from negative 1 to infinity. So the change has been on the range. The domain has not changed. All right. G of t is given as square root of 10 to the power of t minus 100. And we want to come up with the domain. And since it's a square root, that means the index is even. You set this larger than or equal to 0. So I'm going to move this to the other side. And since the base is 10, I'm going to make it 10 squared. Again, 100 is 10 squared. And therefore, t is larger than or equal to 2. We can say 2 to infinity if you want to write it in an interval format. You can write it as such. By the way, infinity and negative infinity always, they take parentheses. For this one, what is the domain? I hope you remember y equals sine x. The domain is all real numbers. And then e also has no restriction. So if you think of this as x, sine x, remember the domain for x was all real numbers. Therefore, you're interested in the domain of e to the power of t minus 1, which has no restriction. Exponential functions, no restrictions on the domain. Therefore, all real numbers. We want to solve for t, and we notice on the left side, e to the power of x squared is being multiplied by e to the power of 2x plus 1, and you can use the product rule. which means the left side, you can add up the exponents. This is the product rule. So when you add up the exponents, they both have the base e. So this must be equal to t. And believe it or not, you're done. So t is the sum of x squared and 2x and 1. That's basically what happens in this example. All right, let's look at logs. As long as we understand the concept that log is simply an exponent, we'll be in good shape. So what I want you to pay attention to before we move on anywhere, I want you to see this one, log x base b equals y. You go with this arrow, because if we can make this transition from one format to the next, we are absolutely comfortable with logs. So I want you to look at this one first. Look at this arrow. B to the power of y is x. That's the meaning of this arrow. If you remember this arrow, you will never make a mistake going from logarithmic format to exponential format. So look at this arrow. B to the power of y is x. So what does log represent? It's just the exponent. Again, just for the sake of argument, if somebody says 2 to what power is 8, it's the same as saying log 8 base 2. What is that equal to? And both of them, as you know, the answer is 3, because you know 2 cubed is 8. So log is simply an exponent, and we have to understand it this way. We have a part in calculus known as logarithmic differentiation, which makes it very difficult if we don't understand log. So log is the reverse part. So let me clean up this. And so just like the exponential functions, the base must be positive and can't be 1. And they are equivalent in this form. I think this really helps if we understand what's going on. So with that being the case, we have a bunch of rules in general. Log 1 with any base is 0. And if you look at this format, some of them can be proved this way, and some of them we have proved it in algebra. So I'm not going to go over that again. Look at this. Look at this. Look at this. Okay, so these are general forms. Okay, so log 1 with any base is 0, log b, base b is 1. This means if the base and the argument are the same, the answer is 1. This one and this one, number 3 and 4 together, are referring to the fact these two together. Logarithmic functions and exponential functions, they are inverse functions, they undo each other. So therefore, log of b to the power of x when the base is b is x, b to the power of log x base b is x. This is the product rule. Log of xy base b is log x plus log y sine base b. Log of x over y is log x minus log y sine base b. In all cases, you have to mention the base b. And log of x to the power of n is n log x, both of them base b, and that is called the power rule, the quotient rule, the product rule. Now, we should be able to transition from one format to the next. In the case of a natural log, y equals ln x, instead of log, anytime we use ln, in essence, it means the following. We don't write it. This means log x base e. By the way, when you write it, you want to make sure this e is not next to g, but rather it's a subscript. That's the meaning of it. Nobody writes it like this, so we use ln. So if you look at the 7 properties, ln1 is 0, ln e is 1. Take a look at this one because the base and the argument must be the same. Ln of e to the power of x is x, e to the power of ln x is x, ln xy is ln x plus ln y, ln of x over y is ln x minus ln y, ln of x to the power of n is n ln x. And logarithmic functions, exponential functions, or inverse functions. We should know the graph, the general graph, and they are inverse functions. Therefore, they make them symmetric with respect to the line y equals x. Another one that we should know, it's a common log where the base is 10. So if you look at this y equals log x or x equals 10 to the power of y, when we write log without the base is 10. Okay, so the first one doesn't change. But the second one, if we are saying these two must be the same, log 10 must be 1. This becomes log of 10 to the power of x is x, and this is 10 to the power of log x is x. So you should be very comfortable with those. I hope nobody has any problem with that. Now, adding a couple more things, this is the change of base formula. Normally, calculators can't come up with the log of just any base. They can handle the common log as well as the natural log. But if you want to go from, you want to evaluate something at a different base, you can go to common log or natural log. By the way, we are not saying log x the same as ln x. We are saying this ratio is the same as this ratio. Finally, if you look at this coordinate, which is 1, 0, let me write it down. It's clear, but let's write it down. This point as coordinates 1, 0. And as you look at this, when it's below the x-axis, the y or ln x is negative, so it's between 0 and 1. At 1, it's precisely 0. And when it's beyond 1, ln x becomes positive. So that's also a good thing to remember. And it comes from the graph. You really don't have to memorize anything. All you have to do, remember the graph, and you're in good shape. So we have a lot of information here. This is the synopsis of logarithmic properties we all should be comfortable with. All right, we want to find the inverse function for f of x equals 4x minus 1 over 2x plus 3. And the process of finding the inverse is as follows. First and foremost, to make it easy, we change f of x to y. It just makes it easy to deal with it. The next step is to interchange x and y. So x is 4y minus 1 over 2y plus 3. Now, right here, we have the inverse. But normally we solve for y to be on the safe side. So how do we solve for that? We do the cross product. So if I multiply this one by this one, I get 2xy plus 3x. If I multiply this by this one, I get 4y minus 1. Since I'm solving for y, I'm going to move it one way or another. It doesn't matter which way. If I move 2xy to the right becomes negative, this becomes negative, 1 becomes positive. So in other words, this one goes this way, this one goes that way. Could I have done it the other way around? Yeah. The only reason I didn't, class, because if I did it the other way around, in other words, if I pick the 4y and bring it to the left, becomes minus 4y and it's fine. Then 3x to the right. So we have minus 1, we also have minus 3x. We have too many negative signs. It doesn't matter, either way is fine. So on the right side, I can factor out the y. I can even factor out 2y, but I'm not interested in that because I want to solve for y class. I'm gonna just take the y. Okay. Again, can I take the 2y? Absolutely. If I'm factoring, that is the proper factoring, but I don't want to do that. So if you divide both sides, by 4 minus 2x, you get the y. Now, if we had moved differently, as it was mentioned here, then we would have got the following class, and that's okay. This is important to see. If you see minus 3x, minus 1, 2x, minus 4, it's the same thing. The only reason I didn't do that, because it would have given me too many negative signs, and I wanted to avoid that. That's the only reason. Otherwise, it would have been fine. Nothing wrong with that. Therefore, f inverse is 3x plus 1 over 4 minus 2x. Now, it is extremely important that you make sure you haven't made a mistake. And to do so, you have to find their composite function, either f o f inverse or f inverse o f equals x. I'm going to leave that for you. So just for the sake of argument, to give you a hint as to how you do that, if I want to find f o f inverse, replace the x with this, which means you end up with a complex fraction, and you should be able to handle it. So replace the x. I will do the first step for you, and then you finish it later on. Let me see if I can. Okay, let me clean up this mess and see if I can. Let's see. Let's go with the blue color. So I'm going to write f o f inverse equals 4 minus 1, 2 minus 1. Here's my f inverse. I'm going to put 3x plus 1 over 4 minus 2x. Three x plus 1, 4 minus 2x. This is a complex fraction. All you have to do, the next step is to multiply by LCD, which is 4 minus 2x. If you multiply the top by 4 minus 2x, the bottom by 4 minus 2x, you come up with the answer. It's very straightforward, everybody. It's not a big deal.
Hey, can you go to example 10 just for a quick second? I just need to double check something.
Okay.
All right, thank you. Yeah, I just want to check something if it was right with my notes. Thank you.
Excellent, Chris. Sure. All right. So we're going to find the inverse function in this case. And the process is We change f of x to y. That makes it easy. We do the cross product. We change the y to x. My apologies first. I thought I did that. And I went from there to there. No. The very first thing, we interchange x and y. At this step, we do have the inverse, but we solve for y, which means to solve for y, we're going to do the cross product. So x times 1 plus e to the power minus y equals 1 minus e to the power minus y. All right, so let's distribute. Now, what we can do to get rid of e to the power minus y, there are a couple of ways. One easy way is to multiply both sides by e to the power of y. So if we multiply by e to the power of y, what happens? This becomes e to the power of y times x. This becomes x. E to the power of minus y and e to the power of y becomes e to the power of 0 or 1, simply x. 1 times e to the power of y minus the product of these two, again, is e to the power of 0 or 1. So when we multiply by e to the power of y, it creates this one. I hope everybody can see this. All right. The next step is to bring everything involving y together. So we are going to move this one this way, this one that way. And on the left side, we can factor out the common factor of e to the power of y. We divide both sides by x minus 1. Now, please understand this has too many negative signs. It's not a big deal if you left it as that. But if you multiply the top by -1 and the bottom by -1, this becomes positive x positive 1. This becomes negative x positive 1. So do you have to make that change? No, but I hope everybody can see that's fine. And now the reverse process of the exponential, if e to the power of y is some expression, you can take the natural log of both sides. Let me use a different color. If you take the natural log of the left and natural log of the right, the left side becomes y. And we call it F inverse. So F inverse is ln of 1 plus x over 1 minus x. And I highly recommend you try F inverse to show this is correct. And that shows the information and knowledge about exponential as well as logarithmic functions and how they work together. We want to write as a single log using those logarithmic properties. Let's see how we do that. So first and foremost, if you look at this one, this is 1/3 ln of x plus 2 cubed plus 1/2, and we have the brackets. Ln x minus ln of the parentheses x squared plus 3x plus 2 to the second power. So first, I hope you realize this 1/3 will cancel out this 3. Because if you have the base, if you have the coefficient, it becomes the exponent. So this 1/3, so this becomes 3 times 1/3. And this, in essence, cancels out this one. So we are going this way. This is the general format. This 1/2, we're going to apply it to ln x. So this, if I cross this out, I can say half of ln x minus half of ln of x squared plus 3x plus 2 quantity squared. So this one becomes ln of x plus 2. This one, this 1/2 can become the exponent. Look at this one, the reverse process. Ln of x to the power of 1/2. This one, if you put the 1/2 here, 2 times 1/2, they cancel each other. So again, this one becomes ln of x plus 2. This 1/2 becomes the exponent. This 1/2 becomes the exponent also, but 2 times 1/2 makes it 1. So what we are looking at now, let me just write this, ln of x plus 2 times x to the power of 1/2 or square root of x. Of course, this can be done in one shot. And if you want to combine these two, because it has a negative sign, this becomes the denominator. However, before we write this, why don't we see if we can factor it? And we are looking for two numbers. The product is 2, the sum is 3, and they are 1 and 2. So x plus 2, x plus 1. And so we can write ln. The numerator is this brackets, and the denominator would be the 2 parentheses. We can cancel those 2. And this is the final answer. This is the final answer. Again, I hope you're comfortable with logarithmic properties. You can practice in case you have a difficult time with that. I'm going to go over the next question. And I need this space, so let me clean up the mess. All right, to do this, we can combine you can do it again in one shot, but you can combine this into ln of x plus y times x minus y. You can make this number 10 the exponent. So this is, so the result will be ln of the brackets over z to the power of 10. As you can see, the product of these two is x squared minus y squared. So this is your final answer, everybody. So one more time, ln of the brackets over z to the power of 10. The brackets is x squared minus y squared. Now, what if we want to go the other way around? What if we want to use the properties of logs to expand? Well, notice this square root means this is to the power of 1/2. The next step, so that's that. The next step is to put the 1/2 in front as a coefficient. So it's half of log of x minus 1 over x plus 1. And as you know, this is log of x minus 1 minus log of x plus 1. There is a 1/2 in front. So 1/2 doesn't go away. This becomes log of the top minus log of the bottom. Log of the top minus log of the bottom. The 1/2 doesn't go away. I want to solve some equations. In this case, ln of x squared minus 1 equals 3. And just by definition, if you assume it's log and it's e here, e cubed is x squared minus 1. Right, this is by definition of a log. So that makes x squared 1 plus e cubed or e cubed plus 1. And so x is the square root of 1 plus e cubed, and it can be both positive as well as negative. And the reason it works, because remember, when we look at the domain, it must be positive. This thing, whether it's positive or negative, when you square it becomes positive, so we are fine. How do we tackle this? You can factor it just the way it is. If for any reason anybody has a difficult time following, you can let's say, any variable except x represent e to the power of x. Therefore, you're dealing with y squared minus 3y plus 2 equal to 0. And just the way it is, you can factor it into e to the power of x minus 1 times e to the power of x minus 2 equals 0, or you can do y minus 1. Let me use a different color. So you may recognize this one as y minus 1, y minus 2. You don't really need to do that. You can go straight to the factoring. It depends on how comfortable you feel with the concept, and therefore e to the power of x is either 1 or 2. So if e to the power of x is 1, if you take a natural log, that means x is ln 1, and I hope everybody knows ln 1 is 0. That also means x is ln 2. So it's important to know ln 1 is 0. One thing I want to add, if by any chance, instead of any of those numbers, we had a negative number, that would have no solutions. E to the power of x equals, let's say, minus 5. Let me just make it up. Let's make up something. E to the power of x, let's say it's minus some, it doesn't matter what number. This has no solutions. This is phi representing no solution, because as you know, the range is from 0 to infinity. I just want to make sure that we know that. All right, I'm going to move on with this. I need this space. So ln of ln x equals 1. So if it bothers you, you can actually literally change this to, let's say, y. So you see how you tackle that. So just change this to some variable of your choice. Okay, so that means if you change it to y, that means y. Okay, so this means y must be e to the power of 1, or simply e. So that means ln x must be E. So if ln x is E, remember the arrow that I showed you, x must be E to the power of E. Anytime you feel uncomfortable with ln x, and as a calculus student, you shouldn't write it as log x base E for yourself, but keep it as ln x, okay, just for yourself. You can write it so you see this arrow that I was mentioning. For part B, we want to solve for x, so we are going to divide both sides by e to the power of x. As you can see, the left side, use the exponential rule, the quotient rule, it becomes e to the power of ax minus bx, and we can factor the x out. Now, you go to the definition of a log, or you can take a natural log of both sides. If you take the natural log, and by the way, why natural log? Because this is e. If you take the natural log of both sides, the left side becomes a minus b times x, and the right side becomes ln c. ln c. If you take the natural log of both sides, or just go by the definition, either way is fine. In other words, go from one format to the next. In this case, from exponential, you're going to the logarithmic format. And so x becomes ln c divided by a minus b. Divide both sides by a minus b. Okay. We want to solve this. ln of 2x plus 1 equals 2 minus ln x. And whenever you want to solve logarithmic functions, basically, if you have a bunch of logs and bunch of numbers, you bring all the logs together, all the numbers together, and you go with the definition. So that means we're going to move this one this way, becomes plus ln x. And we're going to combine this into ln of their product. So now that we have a single log, we go with the definition. Remember the arrow. Let me just draw the arrow. So that means e, the base is e squared is this. Now, of course, this is 2x squared. This is plus x, and we bring them to the same side. Minus e squared equals 0. And we want to solve this. And to solve this, remember, e is not missing. Okay, e is 2.718, and it continues indefinitely. E is a number. So we're going to keep it as e to get an exact answer. So we are going to use the quadratic formula. Everybody remembers the quadratic formula. Ax squared plus bx plus c is 0. X is minus b plus minus a squared of b squared minus 4ac over 2a. We are going to use that. So if we are going to use that, quickly, we want to know what is a, b, c. Okay, so a is 2, b is positive 1. This whole thing minus e squared is a number. That's the value of c. So this is a number. Don't forget this is a number. The reason I'm keeping it as e squared is a precise answer. It's like pi is a precise answer. It's not 3.14, okay? And so now we're going to plug in to the quadratic formula and replace the b with 1, a with 2, c with negative e squared. So just plug in. So minus b, so minus 1 plus minus a squared of b squared, 1 squared. By the way, if it's negative, you want to put it in a parenthesis. Minus 4 times a times c, and then 2 times a, I just wrote 4. 2 times 2 is 4. And as you can see, this is minus 8 and minus positive 8e squared. So that's the answer for x. And going back to the original equation and sticking with that, remember the domain x must be all positive values. We can't have a negative value. So this has -1 minus this mess over 4 and -1 plus this mess over 4. I hope you realize -1 and minus the mess makes it negative. It's not acceptable here. So we only have to use the positive one. So there are two answers here. -1 minus the square root of 1 plus 8e squared over 4 is a negative value, not acceptable. But this is definitely a positive value, and that is acceptable. And of course, it's simple. Definitely, this is larger than 1 and makes this expression positive. All right, we want to look at cosine of sine inverse and prove that it's equal to square root of 1 minus x squared. And to do that, I hope you remember that when we look at the sine inverse or arc sine, they call it that's an arc or angle. So in essence, if you call this theta, you're looking for cosine theta class. If you assume this is alpha, beta, gamma, whatever you want it to be, for example, theta, that's what you're looking for. You're looking for cosine theta. So if you let sine inverse x be theta, by definition, then sine theta becomes x. So if you let this one be theta, that means sine of theta is x. As you know, sine squared plus cosine squared is 1. And that gives rise to various formulas. For example, cosine is plus minus the square root of 1 minus sine squared. Okay, this is one of your Pythagorean identities. So that is the case. And so cosine is one of those two, and we're going to take the positive only. Why is that? Because of the restriction. Remember, none of your trigonometric functions are one-to-one because they are all periodic. So you restrict them. And when you look at sine, the restriction is minus pi over 2 to pi over 2. And in the fourth quadrant and the first quadrant, cosine is always positive. So there are two answers. You take the positive value only. And we just proved that's the answer. Let me erase this. Simplify sine of 2 arc cosine x. And again, remember, arc cosine x or cosine inverse x means the same thing. In other words, this part you can say alpha, beta, gamma, theta, whatever you want to call it. So if you call it theta, then that means cosine theta must be x. That's the meaning of it. So if you call this theta, that means cosine theta must be x. So sine of 2 theta is equal to sine of 2 theta. And what is sine of 2 theta? 2 sine theta cosine theta. Sine of 2 theta is 2 sine theta cosine theta. I hope everybody remembers that. And by the same token that we said sine squared plus cosine squared equals 1. Again, I remind you of that. I should have kept that. So sine squared plus cosine squared is 1. Then cosine is plus minus square root of 1 minus sine squared, and sine is plus minus square root of 1 minus cosine squared. And again, in this case, we keep the positive value because of the restriction. And we like to put the x in front. 2x squared of 1 minus x squared. And the restriction is that you're looking at cosine inverse. And the restriction we put on cosine inverse, it was between 0 and pi. So in the first quadrant and second quadrant, sine is always positive. That's why it works that way.